right, so I wanted to go over the problems that I gave you to look at today during class. And hopefully you'll find out that you did really well. Okay, so the first question has to do with the magnetic field from a long straight conductor. So we would use the expression B equals mu naught I over 2 pi r. That's the expression for the magnetic field due to a long straight wire. And we're asked if you say that at a distance of r, B is equal to B, then what's going to happen if r goes to 2r? Well, if I look at this and I look at the dependence of the magnetic field expression and how it depends on r, I notice that B is inversely related to r. So as r gets bigger, magnetic field is going to get weaker. In fact, it's going to be a direct relationship in the sense that as it gets 3 times further away, B will decrease by 3 times, etc. And so based on that fact, I would select that at twice the distance, the magnetic field would be B over 2, because as we get further away, it's going to get weaker, and it'll be directly the same factor as the increase in R. All right. Here I slipped in a little mathematical problem for you, and also kind of mimicking my love of vectors and vector addition. In this picture, we're also dealing with magnetic fields due to long straight wires. In this case, all our wires are at the corners of a square. The square has sides equal to 1 centimeter, and each of the current carrying wires has a current of 2 amps. And we're trying to find the magnetic field at point P. So we have 3 wires, and one corner doesn't have a wire, and that's where we want to find the magnetic field. So again, just for a reminder, the expression for the strength of the magnetic field is mu naught over 2 pi r. Now, as we've learned, the magnetic field is making circles around the current. And so that means that using the right-hand rule, where we would place our thumb in the direction of the current, so we put our thumb pointing into the page, the way that our fingers wrap around our thumb is the way the magnetic field wraps around the current wire. And so if we look at I3 right here, if I draw a little circle, on this circle the magnetic field will be tangent at different locations to that circle. And so that's what the magnetic field will look like in general around current 3. Now what we want to know is, what is it going to look like down at point P? And I did draw one of these arrows. The one at the bottom really represents what it would look like at point P. And so I might draw an arrow right here to represent the direction of B3. And that'll indicate for the magnetic field due to current 3. Similarly, I can do something like that for current 1. And again, using my right-hand rule, the magnetic field will look like this. As it goes around the circle, I put my thumb into the page, and the way my fingers wrapped is the way magnetic field wraps. And so now here, if I'm trying to think about what the magnetic field due to current 1 looks like at point P, I notice that this would represent it. It's going to be down because it's tangent to the circle. If I drew the circle large enough so that it touched point P, that would be my B1 would be tangent at that location and pointing down. Finally, I have to do B2. Now that one's a little bit trickier maybe, as I draw the arrows around again, because all these currents are in the same direction. It's always going to look the same, but here we're kind of dealing with this different angle, and so we have to imagine the circle being drawn kind of like right here. And so in that case, B2 would be at an angle. It's actually going to be at a 45-degree angle from either the vertical or the horizontal because of the fact that this is a perfect square. So now we've drawn all our vectors, and we have to add them as vectors. What would be useful to know is what is their magnitude. So it turns out that B1 and B2 are going to have exactly the same magnitude because of the fact that they're the same distance away from point P, and all the currents are the same. So I have put in 2 for the current, and then 2 pi, and the 1 centimeter would be 0.01 meters. And so the strength of the magnetic field for those two is 4 times 10 to the minus 5 Teslas. B3 is going to be a little different because of the fact that the distance is a little bit different. This distance right here would be the square root of 2 times 0.01. That's just something we know from 45, 45, 90 triangles. The diagonal there of the square is the square root of 2 times each side. I think I mixed up my rules there, but it's true. So the magnetic field due to current 2 is a little bit smaller because it's a little bit further away. Turns out to be 2.84 times 10 to the minus 5 Tesla. So now I have to add those vectors, add those as vectors, looking at all the x components and then all the y components. So for bx, I have minus b3. Oh, I made a mistake here in my notation. This should say b1 and 3, and this should be b2. Sorry about that. So in the x component, I have minus b3 because b3 is totally in the minus x, and then I have to find the x component of b2, which would be b2 times the cosine of 45. Both of these are negative, and so when I substitute in my numbers, I'll get bx is minus 6 times 10 to the minus 5 Tesla. For by, I'm going to get minus b1 minus b2 sine of 45. Since sine and cosine are the same, and b1 and b3 are the same, this is also going to be minus 6 times 10 to the minus 5 Tesla. B is going to be given by the Pythagorean theorem. That's the total magnitude of this magnetic field. And it's going to be 8.49 times 10 to the minus 5 Tesla. The angle, because my x component and my y component are exactly the same, is going to be the angle whose inverse tangent is 1, which is just 45 degrees. And so we would just want to say that this is below the negative x-axis for that one. All right, so if you got that one, that's awesome because there's a couple things that went into solving that, especially remembering how to add vectors, which you know I want you to remember. Okay, now in this problem, we have to read it carefully and think about what we're doing. We have a long straight conductor with a constant current flowing to the right. That's this wire down here. And then we have a wire rectangle above it that has a current going through it as well. And basically they want us to look at the force acting on each side of the triangle, of the loop, in order to figure out what the net force is, and also to figure out if there's any torque on this loop. So essentially, this wire is creating the magnetic field that the loop is in. So if we use our right-hand rule, we would see that above the wire, the magnetic field would be coming out at us. So we would represent that field like this. And now we want to figure out what is the force on each side of the loop. And to do that, we would be using this expression. Remember, the direction of L is the same as the direction of the current. So if we start at the top and we lay our hand along with our fingers pointing to the left, because that's the way the current's flowing, and then I curl my fingers up, away, or out of the page towards me, then my thumb points up. And so there's a force on the top of the loop that pulls straight up. I'm going to do the same thing now with the left-hand side. This time I'm going to start with my fingers pointing down. I'm going to curl my fingers up at me, and my thumb is pointing to the left. So that's that force. I'm going to do the bottom of the loop. I'll have my fingers pointing to the right. I curl my fingers up out of the page, and my thumb points down. And then finally, I do the right-hand side. I point my fingers up, curl them out of the page, and my thumb points to the right. Now, I've drawn the direction of all the forces, but I haven't really talked about how strong they are. Now, the forces on the left-hand side of the loop and the right-hand side of the loop are going to be exactly the same. What we should understand, though, is because the magnetic field caused by the long wire falls off as 1 over r, the magnetic field that the portion of the loop further to the top or further away, they feel a weaker magnetic field than the portion of the loop that's closer to the wire. So when you're going up and down the left hand and the right hand side of the loop, the force at the top that that piece of wire feels is actually going to be smaller than the force that it feels at the bottom. But when we compare the left and the right, they'll see exactly the same variation. So the force to the right and the force to the left will always be canceling each other out. However, thinking about the fact that the magnetic field is stronger closer to the wire than it is further away from the wire, the force on the top is less than the force on the bottom because of the stronger field as we get closer to the loop. So it actually isn't true that the net magnetic force on the wire is 0, so we can eliminate those pictures. If we remember that the force on the bottom is stronger, then the net force is going to be downward, so we can eliminate this answer. And so basically then we have to figure out, is there a torque? Well, in order to figure out whether or not there's a torque, you have to think about if this loop is subjected to forces first in the horizontal direction and then also in the vertical direction, would any of those pairs of force cause the loop to rotate? And they wouldn't. In the vertical direction, there's a net force down would just cause the loop to move down, and then the forces horizontally are just kind of pulling on the loop to the left and the right. None of these forces are pointing in a direction that would cause a rotation of the loop, so there is no net torque acting on this loop. And so that eliminates this, and we're left with our final possibility, which is the last answer. Okay, this one is one of the tougher questions where we're talking about the magnetic field due to two current-carrying wires, exactly the same current but in different directions. And then we're asked to graph a picture of what that magnetic field might look like. And so I think it's really helpful to draw at least the directions of the fields due to each wire. And this is where, I really think doing some color coding can come in handy. So the wire on the left is carrying current upward. and the wire on the right is carrying current downward. So I'm going to just start with the red wire and think about what the magnetic field looks like to the left of the wire and to the right of the wire. I'm going to point my thumb down and then watch which way my fingers curl. To the left of the wire, my fingers are pointing into the page. So I'm going to indicate that with these X's. So that's the magnetic field due to the red wire. On the other side, to the right of the wire, if my thumb is pointing down, my fingers are coming out of the page. So over here, the magnetic field due to that wire is coming out. Now I'm going to do the same thing with the left-hand wire. Pointing my thumb upward, everywhere to the right of that wire, my fingers are pointing into the page. So I'm going to indicate that field. And if I go to the left of the wire, my fingers are coming out of the page. Now, what I think is really key in helping to solve or pick the correct graph is to understand what the direction into the page and out of the page, what kind of signs they have. If we do a normal axis where this is X and this is Y, we actually would say that X cross Y gives me Z, so positive Z is out of the page, and negative Z is into the page. Now when we're looking at the magnetic fields due to the wire, one of the things that we notice is in between, all the magnetic field is into the page, so that means that it has a Z component, which is negative. However, when we look on the outer edges, what we find is while the magnetic fields seem to cancel each other out, this one is stronger because it's closer to the red wire, which is causing it. And likewise, when we look over here, this one is stronger because it's closer to the green wire, which is causing it. So on these places, the BZ is greater than 0. And so and of course it's going to get less strong as we go further away from the wire. So thinking about those factors helps me choose the right graph. Because if I look at it, the first thing I have to remember is that the magnetic field between the two wires was negative. And actually this ends up eliminating all the graphs but one, because this is the only one that has negative BZ in between the two wires, but it also has positive on the outside, which decreases as we get further away from the wires. And that's why graph number 4 is the correct choice. All right, so this question is basically about Amperes Law, where we say that the integral of B dot dl is equal to mu naught I enclosed. And this is the current that's enclosed by the loop. We use the right-hand rule to figure out what current is positive, and that is if we imagine going around the loop with our fingers going around in the direction of the integral, our thumb will point in the direction of positive current. Turns out for this particular question that's not as important. But in this question we're saying, okay, for the possible loops that are shown here, A, B, C, and D, which ones would have a line integral that would be equal to 0? The key here to figure that out is you want to find the total current enclosed equal to 0. And so right away I see path A doesn't have anything in it, so that's a good candidate. Then I'll notice that path number B has 1 current in it, so that's not a candidate, so B is not an answer. C has current 1 and current 2, and so they would actually cancel out because they're in different directions. And then D has all 3 currents, 2 of which are positive and 1 is negative, so D is not a possibility either. So we've eliminated and found that our choices that satisfy that are just path A and path C. Okay, I think this is the last question. Oh no, it's not. So here is talking about the magnetic field due to in a cylinder of radius r, and it has the current distributed throughout the cylinder. So this is kind of like the problem that we looked at in class. And here's the radius, big R. We found that for a radius bigger than the actual cylinder, the magnetic field would look like a long straight wire. Then we also found that if R was within the cylinder, the magnetic field would look like mu naught I R over 2 pi A squared. So it's actually linearly increases as R, with R, as you go from the middle to its edge, and then it drops off as 1 over R. So that eliminates this choice, this choice, this choice, and this choice. And this is actually the picture that represents it best. And then finally, this one is what happens if you have a solenoid of a length L, it has N windings, and a radius of B. You know, what's going to happen if you double the radius and then if you double the radius, what's going to have to happen to the magnetic field, the radius of the loops? So B for a solenoid is mu naught big N over L times A. And so if the radius was originally B, but it goes to 2B, each winding will take up 2 pi R, where this is of course the radius of the wire. So each winding will take up that. If we double the radius, we're going to double the amount of wire that we use to make each winding. So the number of windings we're going to have is going to cut in half. But if we do that as well, the length of the whole solenoid will also decrease by a factor of 2. And so when you put that into the expression up here, those two changes will actually offset each other, and the magnetic field will remain exactly the same. All right, so I hope those problems you felt helpful. I think the homework problems are good as well. And if you have any questions, shoot me an email.